All right, welcome to the Unit 3 portion of the final review packet. This is going to be based on chemical bonding. I'm just going to put a couple of things here to remember that because we have different ways that these elements form these chemical bonds, primarily ionic or covalent, we just want to make sure that we're comfortable with what those things mean in terms of how these are bonding together. So we know that ionics are formed by the metals and nonmetals together in that order. Metals always come first. That's actually the positive cations with the negative anions, because of course we have polyatomics that aren't necessarily metals. They're a group of nonmetals, and so we have one polyatomic that's a positive, one that's, and then a bunch that are negatives that we use. Metals, nonmetals, no Greek prefixes. So we do not use Greek prefixes when we name these. Roman numerals for transition metal charges. And that's pretty much it outside of just the actual properties, which we'll get to a little bit later. So, of course, covalent compounds, online you might hear these called molecular compounds. Those are our non-metals with other nonmetals. And now because these are nonmetals and nonmetals, remember, nonmetals want to gain electrons. So when I have multiple nonmetals, everything wants to gain and nothing wants to give away like the metals do. So they come to a compromise and they end up sharing. So that's the idea here. And you know what? I'm actually going to add that toward the end here, where there is electron transfer in ionic compound bonding, ionic bonds forming, whereas there's an electron sharing, which I'll get to. I'm going to put everything in the same order. So in this case, we use Greek prefixes. We would say that there are no ion charges, so there's no need to worry about positive versus negative or cations and anions. And then, of course, I'm going to put electron sharing, because that's really the major difference between our ionics and covalents. And now that we're a little bit more comfortable with that as a review, we'll remember, identifying ionic versus covalent, all I have to do is look at that first one. Is it a positive metal or is it not? And if it is, then I know that it is ionic. So sodium is a metal, that's ionic. Carbon is a nonmetal, therefore this is covalent. This is also carbon, covalent. Iron is ionic because it is a metal. So writing the names of these, notice that I have 3 elements in that first one. Anytime I have 3 or more, I know that I have a polyatomic from the back of our periodic tables. We write our ionic names just as the metal. Sodium is not a transition metal, so I do not need a Roman numeral. It always has a positive 1 charge, and that OH group is hydroxide. Next one up, we have a covalent, which means that we're going to be naming using prefixes. We do not use the prefix mono, so like for monocarbon, we do not use the prefix mono for the first element. Only the second, if necessary, which you see that we'll need here. So this is just carbon if it's one of those first elements. And here we would use the prefix mono. And instead of saying monoxide, we just changed and drop one of those O's to monoxide. In this case, because I have more than one of that first element, I do need a prefix, and our prefix for 2 is di. So this would be dicarbon. I do not change the name of any first elements. I do change the ending to IDE if it is a nonmetal by itself. And 6 of these would be hexa, and this would be fluoride. And last but not least, for the naming here, Fe is iron. Now, I do need Roman numerals because I need to identify what the charge is since iron is a transition metal. And so our Roman numerals, remember, are not just how many there are. It is representative of the ion charge that it chooses, the positive charge. So we know that this is going to be chloride, no prefixes because it's ionic. But how do you figure this out? Well, chlorine, we know for sure chlorine has a -1 charge, and we see that there's 3 of them. So 3 -1s create an overall negative charge of -3. And in order to be able to balance that out, this one iron must have a +3 charge because we need the overall charge to be 0. +3 does cancel out -3, and we are good to go there. All right, so then what's my Roman numeral? Well, it's the charge that it takes, which is R3, iron 3 chloride. A couple more formula items. I would really focus on being able to balance those charges like they were up there. Sodium is a +1 ion charge. And carbonate, remember, all of our 8s are indicative of a polyatomic ion on the back of our periodic table. I identify that carbonate has it's a CO3 group with a -2 charge, and the easy way that we identified to create these ionic compounds is by just crisscrossing those charges. So the only time I need to use the charges to create these formulas are for the ionic compounds. This is another ionic because of that metal that I start with, aluminum and sulfite, just like 8s are on the back. Aluminum is a +3 ion charge, and sulfite is actually an SO3 polyatomic group with a -2 charge. And so when you crisscross those charges, you end up needing 2 aluminum to cancel out the charge of 3 sulfates. And you see, because I need more than one of those polyatomics there, I do need to put parentheses because this 3 right here is a part of the polyatomic identity. Therefore, it cannot change. So we need to make sure that note that it sticks together and then identify that there are 3 or however many on the outside that we need there. This is covalent. I know that, one, because phosphorus and chlorine are nonmetals, but also because of the prefixes. Diphosphorus, it tells me exactly how many, 2 phosphorus. Tetrachloride, that's Cl, and tetra means 4. So you do not have to memorize the prefixes, but you will need to know that they mean however many atoms are involved in that bond. And then we have another ionic. I know that because tin is a metal and there are no prefixes. Tin is in this case, because tin could be a +2 or +4, we look at what we're given, and we are shown that it is choosing the +4 version of itself. Phosphide is P by itself for phosphorus. Remember, phosphide is P. Phosphate is PO4, and phosphite is PO3. So again, the suffix changes what those ions are, what the negative anion is. So in this case, it is just phosphorus, and we crisscross, we get SN3P4. 7 diatomics, Honkelbrief, HONCl, BRI, and F. Remember, when they are all alone, we need to make sure that they exist as a pair. They can never be alone. Now, something like hydrochloric acid, that's the chemical formula for hydrochloric acid, but you're like, whoa, I thought you said we needed 2 and 2 if they're there. But remember that since they're together, they aren't alone. So you only need 2 for sure if they are found all by themselves. But they can exist as one, just like here. if they are partnered with something else. All right. So just something to remember. What type of bond is there between carbon and oxygen? Remember, carbon and oxygen are nonmetals. Therefore, this would be a covalent bond. Properties of ionic compounds, we kind of talked about just like the basics up here, but like properties in terms of characteristics and how they act. We did a lab that compared salt and sugar. Salt being ionic, sugar being covalent, and we noticed that a couple things for sure that stood out. Well, there are high melting points, high boiling points, and conductive when dissolved in water. So those are ionic compound properties, just a couple. Those are the main ones there. That's because ionics are strong. Whereas covalents, you can have polar covalents, which are strong as well relative to other covalent bond types. In this case, if we're comparing these two types of bonds, we would consider these covalent compounds weak, which then effectively makes everything opposite, right? So this would be low melting points. There'd be low boiling points. So it was a lot easier to melt the sugar than it was the salt, right? Because the salt didn't even begin to melt, but the sugar melted fairly quickly. So that's what we're talking about there. And then, of course, not conductive at all. And again, that should make sense because covalent compounds are made up of only nonmetals, right? So nonmetals don't conduct electricity anyway. Whereas metals do, and ionic compounds are half metal. And so that's why they don't conduct electricity by themselves as solids, but they do conduct when those ions are separated and the metal ions freed up when dissolved in water there. So that was a real quick overview of Unit 3, and hopefully that helps with our bonding.